Okay, so this quantity here in parentheses is just the difference between a particle's instantaneous momentum and the average momentum. Okay, if we square that and take the average of that, then we get something which is related to our uncertainty in its momentum, or the spread in momentum values. Now, in general, the average value of the momentum does not have to be, it can be any value. For example, the box could be moving to the right, in which case this average value would not be zero. But if we assume that the box is stationary, okay, then that is, the walls aren't moving, okay, then there's no reason for the particle to prefer to move to the right or to the left. Okay, so the average value of the momentum, if you make many measurements at many given times, the average value of the momentum should be zero. Okay, so this term should go to zero, and and so you end up with the uncertainty, or the spread in the momentum squared, is equal to the average of the squared of the instantaneous momentum. Okay. All right. So the Heisenberg uncertainty relationship tells us that delta x delta p is greater than h bar over 2. Here we're talking about a single dimension, so h bar over 2 seems most appropriate. And so if we solve for delta p and then we square that and plug in for delta p squared, we plug in p squared, we get p squared is greater than h bar squared over 4a squared. For a classical particle, that is for a particle which is moving at non-relativistic speeds, then the energy is related to the momentum simply as p squared over 2m. And so the average energy, using this relationship for the average value of p squared, is going to be greater than h bar squared over 8ma squared. All I've done is plugged in the value is plugged in E here. I've just substituted, I've plugged in a 1 over 2m here to get the 8ma squared in the denominator. Okay, so let's take a look at this. This says that just by confining this particle into a box, okay, and giving it the freedom to bounce around, okay, so it's not constrained in the x direction, except that it can't go through the walls. It has to stay within the confines of the wall. That basically tells you that the average energy, has some minimum value equal to h bar squared over 8ma squared. And this is called the 0-point energy. It's basically a quantum phenomenon. It arises from the Heisenberg uncertainty principle, the notion that because we know that we have some constraints on the position of the particle, that means we have put a limit, an upper limit, on the uncertainty in the position of the particle. That means that we have to have a corresponding uncertainty in the momentum of the particle, which implies, for this classical particle, a minimum energy. And this is a very important concept in quantum mechanics. It basically implies that for something like a mass on a spring, which is, after all, something which is constrained in one dimension, right? So you can't stretch the spring to infinity, and you can't collapse the spring to zero. And so it's very much, although it's not these hard walls, it definitely has a mass on a spring has has physical constraints on the distance, on basically the position of the mass. And we would normally think that a mass on a spring, if it's not moving, has zero energy, but here we see that it has a 0-point energy, in fact. If we plug in values for something like an atom has dimensions of about 0.1 nanometers, and so if we actually plug this in, we see that the 0-point energy of an electron in an atom is about 0.1 eV. Okay, this is the one-dimensional case, and it doesn't include the attractive force of Coulomb force, which you'll do in your homework.